5, 4, 3.
This is a homemade rocket engine firing at full thrust upside down next to my laptop. This was a static fire test for a custom solid rocket engine that was designed and built by me and my friend as part of our rocket project. You see, back in February, we decided to build a single stage rocket that would fly to 100 meters by ourselves, which we called Inceptor. Now, this project was by no means an easy one. In order to get the rocket to fly and recover successfully, we needed to develop 3 different areas: the motor, the avionics, and the airframe. In this video, I will be focusing on the motor development, and more specifically on how we're able to reliably test the motor, which is the part that I mainly worked on. Now, people who are involved with rocketry might know that it is a bit unusual to design and manufacture your own motors for rockets. In this case though, we didn't really have a choice. Where we live, rocketry is not a hobby a lot of people do, so purchasing ready-made rocket motors is basically impossible. This left us with only one option: to make them ourselves. To test the engine, we needed to measure one major thing: the thrust it created. So I had to build a test stand that was capable of igniting the motor and measuring its thrust output. There were 2 main limitations: it had to be cheap and it had to be built fast. The main component of this build is a load cell, which is essentially a piece of aluminum with 2 strain gauges glued to the top and bottom that measure how much the aluminum deforms when the weight is placed on it, and convert that into an electrical signal. So I started out by modeling the load cell in Fusion 360 and then modeling a stand for it out of 1 centimeter thick wood. I chose wood because it's cheap and I already had a bunch of it laying around from a previous project. Next, I modeled a holder for the motor that would be 3D printed. Of course, the motor holder is only attached to the load cell, since all of the force of the motor needs to go through that to get accurate measurements. To build the stand, I started by cutting out all the pieces according to my CAD model. I then sanded the side pieces and attached everything with super tiny M1.5 wood screws. I also cut the hole in the middle for the engine and drilled the screw holes for the load cell attachment. If you noticed, the CAD model also had this cross-shaped base. I designed this to add stability to the system, even though in the end we didn't really need it. This tiny board has a built-in ADC, or analog to digital converter, and converts the load cell output to something that can be read by an Arduino. I then screwed the load cell into the stand and quickly wired up the Arduino for a quick test. After making sure everything was working, I proceeded to screw the Arduino on the side of the stand. I also screwed in a relay board that was going to allow me to ignite the motor using this 3.7 volt LiPo battery. Using a relay instead of a fuse means that the motor can be ignited electronically from the computer, allowing finer control and ensuring that logging has started when the motor is ignited. The rest of the electrical connections were made using pretty standard breadboard jumper wires. Now, about the code. The code for this is very simple. All it does is zeros the load cell on startup, runs a 10-second countdown, fires a relay for 1 second to ignite the motor, and then starts reading the load cell data. I used a HX711 library for Arduino, which is designed to make reading load cell data much easier and reduces the complexity to a few simple functions such as tare, which zeros the scale, calibrate, which calibrates to the load cell to the specific units that you want to read, in our case newtons, and of course measure, which reads the force on the load cell. By using these functions, it is easy to program the entire test sequence.
Okay, this is the first test of the igniter and the whole sequence.
Now, the biggest problem with this system is that the thrust data is logged to the serial monitor. So for the data to be recorded, a computer has to be connected. and that's what my laptop is doing there on the side, inside of a cardboard box. This is because I did not include an SD card reader that would allow me to log the data and then read it afterwards. So I ended up just, placing my laptop next to the test stand and hoping the engine would not blow up and kill it. That being said, here's the first test. I did it. I'm doing it.
Okay, test 2, solid motor. It's loading the file. 10, 9, 8, 7, 6, 5, 4, 3.
Overall, this solution worked pretty well, and the data we got from it allow us to simulate the rocket flight reliably. From these simulations, we were able to refine the motor and test again in order to reach our target altitude of 100 meters. From the first test, we realized that our engine was not producing enough thrust to reach our altitude goal, so we ended up doubling the fuel contained and switching to aluminum casing for a lighter motor. After making these changes, we set up the stand for another test.
10, get out of it. 9, 8, 7, 6, 5, 4, 3, 2, 1.
From the data, it is obvious that the motor produced almost double the thrust, both in peak force and in total impulse. This was way more than enough to reach our 100-meter target, which gave us extra weight budget for the final rocket, in case things turned out heavier than we anticipated. Now, obviously this 10-stand design is not ideal, and will not be able to support stronger and larger motors, but for a quick solution, I think it performed surprisingly well and gave us the data that we needed.